Thanks for watching this screencast. The objective of this screencast is learners will be able to graphically determine the number and type of zeros of a polynomial function. So we're going to talk about the fundamental theorem of algebra. You know, the word fundamental means basic or important. You know, the important theorem of algebra. So if p of x is a polynomial function with degree n is greater than 0, of course, then that function p of x has at least one zero in the complex number system. Notice the word complex there. They're not saying that every polynomial function has real zeros, but you know that every real number is really a complex number. So this is the classic statement of what is known as the fundamental theorem of algebra. Every polynomial function has at least one complex zero. We can do a little bit better than that. I'm going to show you what we will use foundationally, and I call it the stronger fundamental theorem of algebra. So it's stronger. It's the one that we'll use. It's a formulation of this that we will use in this learning target. Simply, it states this: every nth degree polynomial has exactly n zeros. No more, no less. If you have a fourth degree polynomial, like x to the fourth plus 2x cubed, doesn't really matter what I write here now, does it? Minus 5x plus 8. How many zeros would that have? Exactly 4. No more, no less. I'm not going to write it on the screen, but if you had a 10th degree polynomial, it has 10 zeros. Now, some of those zeros are real zeros. Some of them happen to be complex. Some of them aren't even unique. Some of them appear more than once. You could have what's called a double zero. In other words, that same zero appears more than once. And if you look at the graph of the polynomial function, those will occur wherever the graph of the function touches the x-axis but does not cross it. And we'll see that in a couple of examples. So here's an example of the type of problem you need to be able to solve in this learning target objective. It says, using a graphing utility, describe the zeros of the polynomial function right here. We're going to look at a graph of this. We're going to use Desmos for this. You could use the graphing calculator if you would prefer. But the function is f of x equals x to the fourth plus 3x cubed minus 15x squared minus 19x plus 30. So we want to answer these four questions. How many total zeros are there? That's an easy one. This is a degree 4 polynomial. The answer is that there are 4 zeros. Has to be. Now, how many of them are real? Well, we better look at Desmos. Start graphing. And let's type it in there. Okay, here's Desmos. I have graphed the function. You can't see it here on the screen, but I'll scroll back. I typed in f of x equals. You can type y equals if you'd rather. You probably also could just leave off the left side and just write the right side, but it's a good habit to get into to use the whole expression you're graphing. So I've graphed the function, and I'm looking for the zeros. I'm looking for the y-intercepts. These are the same as the real zeros of the function, and I see 4 of them. In fact, that's exactly how many zeros the function has. 1, 2, 3, 4 different zeros. So the answer to the question is, how many real zeros are there? They're all real. 4 zeros. 4 real zeros. The real zeros are the ones you can see these. This is the note I would make. You can see these on the graph. Okay. Now the question is, how many complex zeros are there? Well, if there are 4 zeros and all 4 of them are real, then there are no complex zeros. They're all real. And the last question is, what are those zeros? Let's go back and look at the graph again. The zeros are just the x values. So we've got -5, -2, 1, and 3. So we've got -5, -2, 1, and 3. Okay, here's another example. This time the function is f of x equals negative x to the fifth plus 5x to the fourth minus 7x cubed plus 11x squared minus 12x minus 36. I originally had it as plus, and I realized that was a typo on my part. So how many total zeros are there? This many. 5 zeros. How many of them are real zeros? Well, for that we're going to have to look at the graph. So here is the Desmos graph. I see two different zeros. I see -1 and 3. But I also see that at 3, the graph does not cross the x-axis. It merely touches it and then goes back the same direction it came. That's a double zero right there. So really, this is 1, 2, and 3. This one counts twice. 1, and since this is a double zero, 2, 3. This one has 3 zeros. 3 real zeros. One of them is a double zero. Sometimes we also call that a double root. So if 5 of them are in total and 3 are real, how many are complex? Well, they're the other 2. These 3 numbers should always jive with one another. If your number of real and complex zeros don't add up to the total number of zeros, something ain't stirring the Kool-Aid, Ace. And what are the real zeros? Well, they're -1 and 3. And if you want to indicate that that was a double zero again, you can. Alright, you know what time it is. It's your turn. Pause the video. Hopefully you'll use Desmos or your calculator to look at a graph of the function. So try this out. Hit pause, look at the graph, and see what you come up with. Let's check this out. Let's look at a graph of this on Desmos. Before I do, I know the number of total zeros. There are 7 zeros total. How do I know? Well, it's a 7th degree polynomial. But how many of them are real? The graph of the polynomial function shows only these 2, -3 and 0. 0 is a double root. So 1 and 2, 3. There's only 3 real zeros. Maybe we should go ahead and list those. We had -3, and we had 0, which was a double zero. So if there are 3 real zeros and 7 total, how many are complex? It's 4, yeah. There are 4 complex zeros in this function. Thanks for watching.